This is project 1.5, the counting circuit. This circuit uses a combination of special operation chips and normal logic gates. The circuit uses an important function, clock signal or oscillation. The first circuit uses an important function called button input. This function has two varieties, and that has a pull up and a pull down input. This allows for either a high or low input to start, and when the button is pushed, that output is reversed. The next part to this circuit is the NGO, or the NAND gate oscillator. This circuit uses two RC mini circuits. The first one is shown here. When the button is pressed, the first capacitor will fill up, and when the button is released, will discharge into the next NAND gate, which will cause the LED to stay on for a prolonged period. The period is determined by the size of the capacitor and the size of the resistor in the RC circuit. The second RC circuit is shown by the red highlight. The capacitor works similarly, shown in the diagram here. Due to the placement of the resistors and the gates around it, it can fill up and discharge rapidly. And due to the nature of logic gates, of only having an on and off output, it will flash instead of fading in and fading out. The next stage is the decade counter 4017 special operation chip. This chip takes the clock signal from the previous circuit and changes it into a 10 outputs, 9 normal outputs, and 1 carryout output that is active for 5 out of 10 clock pulses. This can be used in combination with other chips to increase counting range. The chip's outputs can be visualized here, pairing with each up and each down of the clock signal. In real life, this can be seen with a 10 LED bar graph, as seen here. The LED on the side represents the carry out, which will be on half the time. The next stage of this circuit is the 4510 special operation chip. This chip takes the clock pulse from the 4017 and turns it into 4 binary outputs. Each of these LEDs have a different binary weight, such as the Q8 has a weight of 8, the Q4 has a weight of 4, the Q2 has a weight of 2, and the Q1 has a weight of 1. This allows for counting in binary, as seen here. Now, based on the previous two RCs, increasing or decreasing the capacitors can increase or decrease the speed of the LEDs flashing and the duration of their flashing. In this circuit, I've swapped between the 103 and the 104 capacitor. Here I am changing whether it's an up or down count by slotting my switch to the up-down pin on the 4017. Here I use another pull-down switch to enable the reset pin. This resets the count to 0 and starts counting all over again. This chip takes the 4 binary counting outputs from the 4510 and converts them to 10 decimal counting outputs with the 4511. This chip is sequential due to its storage component. These 10 outputs labeled A to G go directly to the 7-segment display, which is 7 individual LEDs, each of them also labeled A to G. All of these things put together, soldered and cased, will end up looking like this. Thank you for taking your time to watch my video. I hope you enjoyed it.